Welcome to lecture 43, support vector machine, continuing. Under module 9, predictive safety and risk analytics 2. We will start with the performance measures of support vector machine for the separable as well as linearly non-separable cases, and then we discuss if linearly non-separable case arises, so how to handle it, and if the separation is not possible linearly, so how to handle such nonlinear support vector machine. Last class I discussed about training data, test data, and then we have shown you that the mathematics, but primarily the mathematics behind support vector machine, and with an example we have discussed that how the new data points can be classified. When you use test data, you can also check the model predicted values vis-a-vis the actual values. When you use test data, you can also do the same thing. Here we are concentrating on the test data. We are and we are checking whether what is the accuracy. So as we are dealing with two class problem, so the classes actual label will be either yes or no, or class 1, class 2, or class 0, 1, and similarly predicted labels will be yes, no, class 1, class 2, 0, 1, or positive, negative, something like this. When the actual one matches with the predicted one, like both yes, yes, or both no, no, then what will happen? When it is yes, yes, or positive, positive, we say true positive. When it is no, no, or negative, negative, we say it is true negative. But the other two cases, when actual one is suppose positive, but prediction is talking about negative, then it is false negative. And on the other hand, when actual is negative, but it is predicted as positive, that is called false positive. So that means in the test data, whatever level of data you consider, so suppose the n data points consider, then the n data will be sum total of true positive plus false negative plus false positive plus true negative. So true positive plus false negative plus false positive plus true negative. Using this information, you will be able to compute accuracy, which is true positive plus true negative by the total number of observation in the confusion matrix. You can compute precision, which is true positive by true positive plus false positive. You can use recall, sensitivity, which is true positive rate, that means TP by TP plus Fn. So TP by TP plus Fn, so that means this NES from the actual occurrence. If I say this is rho, we can say N plus, N1 plus, and this will be N2 plus. So similarly here this is N plus 1 and N plus 2, something like this if we create. So TP plus Fn, TP plus Fn, TP plus Fn is the basically here row total and TP. So that means actual what is the predicted proportion of actual positive prediction out of the positive samples. Similarly, what is the proportion of the true negative out of the negatives. For example, here if you see specificity, the true negative rate, that is true negative. Which one is true negative? This is true negative divided by true negative plus false positive. So that means in actually, suppose we have N2 plus number of negative samples, And then what is the specificity here? Specificity is how much is correctly, what is the proportion correctly predicted by the classifier. So these are the accuracy measures which are used. Apart from this, there are F1 score, some more measures are there. So you can Google it, or you may get all those things from other books. And these measures range between 0 to 1, and obviously higher the value, greater the model. Another measure used in classification is known as ROC curve, and this ROC curve for basically two class or binary classifier. The ROC curve, actually you just see that it basically, it's a plot of between false positive rate, that means specificity, versus true positive rate, that is sensitivity. So specificity and sensitivity, if you plot, you get this kind of curve, and the area under the curve is the measure of the I can say the model predictive power or accuracy. So here the larger the area under the curve, better the model. Okay, so these are the things you also should know. Now we will discuss something on the another group, what is basically non-separable case. Earlier I said to you that no observations or no samples will fall between the margin to margin edge hyperplanes. In between two margin hyperplane, there will be no sample values or no observations. Here we are talking about, suppose we consider B1 is the hyperplane, and B11 and B12 are the margin edge hyperplanes. Now we are using this for classification. So, but here you see that P this point as well as Q this point, they are basically out opposite, not in the correct side of the hyperplane. This is the hyperplane we are looking for. But if I consider this, then this circle should be right hand side and this square should be in the left hand side of this, but this has not happened. But within the, if we consider the two margins, other points basically, other positives and other negatives and positives points, they are well separated, but only few points may be like this. So that means some points will be within the margin edge hyperplanes. So this kind of situation is basically non-separable case. So how to do it? How to I can say take care of this situation so that the classifier will be able to classify a new observation correctly. So in order to do so, that the concept is you introduced a slack variable. The slack variable you introduced to cater the problem. What is the problem? These are not linearly separable. Some points are within hyperplanes and certain points are basically, they consider the main hyperplanes, then the some points are in the on the opposite sides where it should not be in consideration to completely separable case. So the slack variable is introduced for the positive samples, the slack value will be subtracted. For the negative sample, slack value will be added. So that means the original these two I can say the equations, the two margin edge hyperplane, that those equations, they were now adjusted with the help of slack variable, which is subtracted for the positive sample and added for the negative sample. Now if you consider this modification, then the equation which the primary equation, or I can talk about the constant point of view, that will take this kind of function. So what is the difference? Here right hand side 1 minus xi xi is basically the slack variable, and in this case the objective function is also changed. So earlier objective function we see this portion, now additional portion is plus I equal to 1 to n xi I to the power k xi I for the slack variable. Now k can be any value, but for simplicity k is considered to be 1. So that means what are you finding out, that in order to develop the program, your mathematics is little bit changing here, and you have introduced slack variable to cater the problem related to non-separable case of this nature what we have discussed so far. And then your objective function is having one more term for the slack variable, and also each of the hyperplanes as well as the joint equation, the constant also changed, or it basically takes into account the slack variable. So with this I want to explain the meaning of slack variable. Okay, what actually slack variable measures? Slack variable measures the deviation of a data point from the ideal conditions of pattern separability. What ideal condition we assume? We assume that the ideal condition will be that completely linearly separable, but that is not taken care of. So now what happened? It is not completely separable. Some observations are within the marginalized hyperplanes, maybe basically that they are basically on the opposite side of the hyperplane, and so this deviation to be taken care of. If you want to do this, then slack variable is introduced, and slack variable is the measure of that deviation. Now if the slack variable for in between 0 and 1, then it talks about that the data point inside the region of separation, but on the correct side of the decision surface. Okay, suppose if this is the decision surface, xi value is in between 0 and 1, then some values that this kind of, that means circle squares, here some basically circles, but see they are on the correct side of the class. So the square class and circle class, or positive or negative, or class 1 and class 2, if you consider this with reference to the main hyperplane, they are on the correct side. But if xi greater than 1, then it basically talks that the data is on the wrong side of the hyperplane. For example, here this point should have been this side, but it is in the wrong side. Similarly, this point which should be here, but it is in the wrong side. So that is the reason the slack variable is introduced. So in order to capture this phenomena properly, because in real situation you will not get completely separable, linearly separable case, you will be having such kind of that behavior, that some examples will be in the opposite side. Okay, so the meaning of I can tell you that slack variable you understand now. Now how to find out the value of slack variable? That also formula given here. Just you can use this formula, which is maximum of 0 d minus yi, that particular equation. So okay. Now if the margin introduces slack variables, or I can say if the margin contains that observations, then this kind of margin is called soft margin. Okay, so that means what is soft margin? A soft margin is one that incorporates slack variables. But if it is completely separable, suppose no data points inside, so then you can say this is hard margin. So in hard margin, nothing will be there in between this within this margin. Soft margin, yes, things will be there. So soft margin case is tackled using slack variable. Slack variable quantified using this formula. Slack variable changes the equations by introducing appropriate parameters or terms in the equations. That also you have seen. Now let us see that what are the changes taking place in the mathematics. First, I told you that our minimization problem with completely separable case was this. Now additional this portion added. Our completely separable case, the constraint was this one. Now in the constraint, this part is added in the first constraint. In addition, another constant for slack variable, non-negativity constant, is also added there. So from one constraint to two constraint, and with modified equation you got it. Your objective function also have one more term. And now this is basically nonlinear problem. So as nonlinear problem is there, so like previous one, nonlinear problem, so we use Lagrange multiplier, and then the equation for Lagrange multiplier will actually be similar to the separable case, completely separable case, but additional part is that the slack variable and the terms are added there. Procedure is basically now take the derivative of this equation and put to 0. Now instead of two equations you are getting three equations, w with reference to w and lambda, then lambda and y, and lambda and mu. These three equations you are getting. You will not be able to I can say estimate, because w is required to be estimated because the lambda is not known. So in order to know lambda, so you have to follow the few more steps like KKT condition and this KKT condition. So now the primal problem will be converted into dual problem, and then finally quadratic programming will be used, and you will be able to find out the lambda. Once lambda value is computed, then w value can be computed because you know the other values. So once w is computed, so w is known, then b will be known, and this type of equations we have shown you in the previous lecture also. So the positive and negative examples also I have shown you very clearly. Classification, that the algorithm, or I can say rule, are the same. If you, for a new observation, you put into this equation. In this equation you put the z value. Okay, so here you put the z value, and if you find that this value is greater than 0, it will go to the group 1 or the positive one, and other one is the negative one. Okay, two class case. So but this can be used for multi-class case also. So we are showing the examples of two class problem to you. Another issue is basically that means we have now completed conceptually two things: completely linearly separable with hard margin, linearly separable with soft margin, introducing slack variable. Now the situation is where you cannot linearly separate them. That will be because the features are such that, variables are such that the way they are related, they cannot be linearly separated. So and because they are non-linearly related in such a manner, you cannot separate them linearly. So under such situation, what is required? You have to use some kind of function or transformation function which will help you in separating them. So this, for example, here you see this is the case. Here you see that positive, if plus is positive class, that plus class this side, and in between the dots are there. Okay, so now, so if you go to right or left, up and down, ultimately you are basically seeing that the plus class is towards right and towards left, both places it is there. So it is not a linearly separable case. So what hyperplane you will, which is the support vector, what hyperplanes you will make. Now, okay, if you just do little bit of transformation here, what you will do, you will write here x and x1 as it is, and x2 if you square. So if you make x2 square, yes, I think this is x2 square. Then you see that what is happening here. Your data set is something like this. So I think, okay, this is perhaps this is the different examples. Different example, this one. So okay. So because number of observations are many more here. Okay, no problem. Sorry. So here also you see that in the second example you see the dots are here in between and the squares are out or rectangles are out of this. So this also not a linearly separable case. Then how to make them linearly separable? For example, here in this particular case, if we do some kind of transformation, that means first we take x1 as it is and x1 plus x2 to the power 4, if we create another variable and use this x1 and x1 plus x2 to the power 4, so see that you are able to get a line which is linearly separating the two class of observations. In this case, if you do another some transformation like this, x1 square, from x1 you are creating another variable x1 square minus x1, and from x2 you are creating x2 square minus x2. So then you just see you are able to get linearly separable case. So this is x2. Okay, so let me repeat. We have two example, one example 1 here and here example 2. And in example 1, you say this, the points are such that there is no linearly separable hyperplanes. So you converted the data in this manner, x1 as it is, x2 is used along with x1 to create another variable x1 plus x2 to the power 4, and then it is linearly separable. And for the second example, similarly, x1 is converted to x1 square minus x1 and x2 is converted to x2 square minus x2, then that also giving you another linearly separable case. So what are you doing? You are basically, in order to make them linearly separable, you are transforming the data to higher dimensional space. x1, x2, 2, you have seen that x to the power 4, here x square terms, these things you are doing. If you do this, your that hyperplane you will be able to create. In search of hyperplane, here is this hyperplane, here this hyperplane, you will be able to create it. In order to do so, the mathematics obviously will change, and that the concept part I will discuss now. What is the change in the mathematics? So first of all, the objective function is this, but when we talk about the constraint, instead of xi we are writing phi xi, because phi xi is the transform variable for xi. Rest of the things are same. So you have to have the search to find out the appropriate phi xi, which will make the two class problems linearly separable. Okay. Then W, the procedure again remains same. Once you know this, the procedure, the similar approach will remain same, and by doing that kind of computation, you will be able to find out the W value. Once W value is known, B value you will be able to find out, and fine, B and W is known means the hyperplane is known. So this is what I can say the conceptual part of that support vector machine is over. Again, let me tell you, in this case also, actually I should have told you in the beginning. Basically, this is also based on the book by Tan et al. 2005. So, based on this. With this, I hope that I have given you some idea related to the nonlinear support vector machine as well as linearly non-separable case by introducing many things, including the slack variable concept, transforming xi to phi xi concept, and these concepts are valuable for all of you. So, the references, as I already told you, that the primary reference is this Tan et al. And from the some data points of view, we basically looked into our own work. That is what for this lecture today. Thank you very much for your patience and kind listening to my lecture. Thank you.